Okay, so let's start. So yeah, today's topic is second order linear ordinary differential equation. Okay, so you will frequently see this kind of differential equation if I talk about the second order. Okay, and if r of x equal to 0, then suppose it's equation number star, then its second order homogeneous linear ODE, and if r of x not equal to 0, then is second order non-homogeneous linear ODE. Okay, so there is a theorem. It says if y1 and y2 are solution to any homogeneous linear ODE, then its linear combination of that ODE is also the solution. Okay, what it says is, suppose y1 and y2 is the solution of ODE which are homogeneous. You have to be very careful here. Homogeneous term, that has to be homogeneous, which means that Rx must be 0. Then the linear combination of y1 and y2 will also be the solution of that homogeneous linear ODE, which means that suppose y1 is the solution, which means that what I can write y1 double dash plus px, y1 double dash single dash plus qx, y1 equal to 0. Suppose it is equation number 1, since y2 is also the solution. Suppose it is equation number 2. Then this theorem says that the linear combination, which means that y equal to c1 y1 plus c2 y2, will also be the solution of that differential equation. Okay, how can we prove that? Suppose that differential equation clearly is, you can see that differential equation is what, y double dash plus px y dash plus qx y equal to 0. Okay, so this is this is that differential equation. Can you tell me whether it is a homogeneous or non-homogeneous? Can someone tell me? Homogeneous or non-homogeneous, this equation? Tell me. So you guys will not say anything, huh? It is a linear or non-linear?
Linear, sir.
Why linear? Because you can clearly see that you can write this form of the differential equation in the form of this. Why? Because I know that y double dash means that operator is d square y, okay, and px and y single dash means d raised to the power 1 y, okay, plus qx y equal to 0. Since you can see that right hand side is 0, okay, I clearly told you if Rx equal to 0, which means that that differential equation is homogeneous, okay. So that's why it is a homogeneous. And why it is linear? Because I can write this differential equation in the form of this. Now you can see that I can write like this. So this is what Ly equal to 0. That's why it is linear, okay. But this is not the our question, okay. Now what this theorem says that if y1 and y2 both are solution to any homogeneous differential equation, then it's linear combination. And what is that linear combination? This is the linear combination of that solution. So it is saying that this linear combination will also be the solution of this differential equation. So how will I prove it? You can see that if this is the solution, then I can write y dash equal to what? C1 y1 dash plus C2 y2 dash, okay. Similarly y double dash will be what? C1 y double dash plus C2 y2 double dash, okay. Now plug these two into this equation, then you will see that C1 y1 double dash plus C2 y2 double dash, okay, plus px C1 y1 dash plus C2 y2 dash plus C1 y1 plus C2 y2 equal to 0, okay. Now if you take common C1, then I can write y double dash plus px y1 y single dash plus qx y, okay. Similarly if I take common as a C2, then I can write y2 double dash plus px y2 single dash plus qx y2 equal to 0. Now you can see that since y1 is also the solution, which means that this equation satisfies, so that's why this one will be 0. Similarly C2, this one will also be 0 equal to 0. So 0 equal to 0, which means that this linear combination will also be the solution of that differential equation. So this is what that theory says, okay. Now is there any doubt here? Okay, so let's move forward. That is initial value problem. So it says for second order homogeneous linear ODE, then in short it is also says IVP, okay. Initial value problem is IVP. So it says that IVP consists of two initial condition. And what are those? It says y x naught equal to k naught and y dash x naught equal to k1. And this initial value will actually help to determine two coefficients. And what are those? C1 and C2. From where? If you get the solution of the linear combination C1 y1 plus C2 y2, which means that if you have two solutions y1 and y2, and if you write linear combination of those two, then this initial value condition will actually help to get C1 and C2. So that kind of problem will call as a initial value problem. Okay. Now if you have one solution, now if you want to get another solution, what I meant is, suppose you already got y1, okay, now I want to get y2, then how you will get it? So that kind of problem is called reduction of order. Okay. For example, suppose if you have one differential equation is like this: x square minus x y double dash minus x y dash plus y equal to 0. Okay, so this is one differential equation, and I already know that if y equal to x, y1 equal to x is one solution. Okay, one solution. Okay, now I want to determine what is y2. Okay, then in that case what I will assume is, let y2 is a kind of solution of this form. Okay, I'm assuming that y2 will be another solution to this differential equation, and that is of the form u times y1, which means that I can also write u, and what is y1? X. Okay, I'm assuming that the second solution is u times x. Then I want to get what is y2. And you guys have to understand here is always y1 and y2, all these two solutions has to be linearly independent. Okay, and how to can you guys tell me how we will get to know that y1 and y2 are linearly independent? I told you in the linear algebra class, if you have two functions y1 and y2, and you want to know that whether these two are linearly independent or dependent, how can you know that? Tell me. In the linear class, I told you about Wronskian. Are you able to recall it? Wronskian? Wronskian is something like this. It is a determinant. It is a determinant of this form. Suppose you have two functions y1 and y2. Then the first row will be y1 and y2, and the second row will be derivative of y1 and derivative of y2. Okay, if w equal to 0, which means that if Wronskian is 0, then y1 and y2 are linearly dependent, and if w is not equal to 0, which means that y1 and y2 are linearly independent. So in second order differential equation, there is a condition. If you have two solutions, which means that both two solutions has to be linearly independent, otherwise you have to find another solution. Here you can see that this is one solution of this differential equation. Now I want to know what is other solution, because it's a second order differential equation, which means that it has two solutions, and both solutions can be written as a linear combination. And if we already know that this is one solution, then we have to find other solution such that both solutions are linearly independent. That's why I'm assuming that if y2 is u times y1, okay, so you can see that here y1 and y2 is clearly linearly independent. You can check it. Okay, now since we have assumed that other solution is second solution is y times y u times y1, now what will I do is I will plug this into this, then I will try to get u. Okay, because first solution we already know. Okay, then I will try to find u. Okay, what will I do? I will plug this into the first into the differential equation. So I have assumed that y2 equal to u times y1, which means that that is nothing but u times x. Okay, then what is the first derivative? First derivative y2 is what? U plus u dash x. Okay, and what is second derivative? Second derivative will be u double dash u single dash plus u double dash x plus u single dash, that is nothing but u double dash x plus 2 u single dash. Okay, now I'll plug this and this into this differential equation. Okay, then you will get x square minus x, and what is double dash x? That is u double dash x plus 2 u dash plus minus x. Here it is minus x times y dash. Okay, x times y dash, and what is y2 dash? I'm putting y2. Okay, because I'm assuming that y2 is the solution of this equation. That's why I'm substituting y2. Okay, y2 single dash, that is u plus u dash x. Okay, and plus y, so which means that that is u times x equal to 0. Wait 1 minute, someone is at my door. Wait just 1 minute. Okay, so what will I do is I will separate y double dash like this. You can see that I can write x square minus x u double dash plus x square minus 2x u single dash x, and other terms will be cancelled out. Okay, now I will assume, you can see that it has reduced to second order, but there is no such term like u, which means that I can assume u dash equal to v. So I can write x square minus x v dash. Okay, because I have assumed that u single dash equal to v. So at the place of u double dash I can write v dash plus x square minus 2x v equal to 0. So here you can see that there is a reduction in order. Okay, now as you already know that I can write at the place of v dash, this is nothing but dv by dx, and here I can send it, that is x square minus 2x times v. Okay, now so I can write dv by v equal to minus x square minus 2x divided by x square minus x and dx. Okay, now I will integrate both sides. So this will be ln v. I will write mod, because in logarithmic the value inside the log should always be positive number. Okay, so that's why I have taken as a negative, taken as a mod. So you can see that I can also take a common of x, so that will be x minus 2 divided by x times x minus 1. Okay, dx. Have you any doubt? Okay, here actually it should be cube. it should be in the problem, I think it's a cube. Here it should be cube. If you simplify it, it will become cubic. You can see that it is a x more, so it will be cube. So it will be cube. So that will be take common. It will be 2 only, but here it will be a cube. Okay. So then that will be x times x minus 1. Okay. Then ln v equal to, if you use partial fraction, then what we'll get? If you use a partial fraction, then you will get something like this: 1 divided by x minus 1 minus 2 by x dx. Okay. Then ln mod v equal to, this will be ln mod x minus 1 minus ln 2 times ln x, okay, plus c. So this will be ln v, and here I can write mod of x minus 1 divided by x square plus c. Now I can transfer this side, so you will get ln v divided by x minus 1 times x square equal to c. So you will get v x square divided by x minus 1 equal to, since it will be ln c, so I will consider another constant, that is k. So you will get v equal to k times x minus 1 divided by x square. So this is v. This is v.
Hello, there will be e to the power c, no?
Yeah, sorry, e to the power c. So it should be e raised to the power c. But anyhow, that will be a constant. Okay. Anyhow, it will be a constant. So I can write k times x minus 1 divided by x square. So this is a v. Okay. But we have already assumed that v equal to what? U single dash. So what will I write? V equal to u dash equal to k times x minus 1 divided by x square. So which means that I can also write du equal to k times integral x minus 1 divided by x square dx, and here it's all will be integral. So you will get u equal to k times, so this will be 1 by x minus 1 by x square dx. So you will be k times ln x, okay, plus what will be what? 1 by x. Okay. There will be another constant also, but I will tell you that will be absorbed when we will use the linear combination. Okay. So this is the u. Okay. So what will be the other solution? I already told you that will be x times or u times y1. That will be, what is u? You already got that. So it will be k. Okay. What is y? X. So that will be k times x ln x plus 1. So this is the solution. This is the second solution, which means that I can write in the form of linear combination. So what will be the general solution? General solution will be c1 times x, that is c1 times y1. I will write c1 times y1 plus c2 times y2. So that will be c1, and what is y1? That is x. c2 times, I can also see that c2 times k, that will be a single constant. So instead of that, I will write c2. So that will be x ln x plus, that you can see that will be phi1. So that will be a solution. So this is the general solution. Okay. So you can see that these two are actually linearly independent. If you write Wronskian of this and this, then W will not be a 0. So that's why it is a solution. Fine. Any doubt here? Tell me.
No, sir.
Okay, so based on this you can always able to find the solution if you have one solution. Okay, similarly I can apply this thing, this explanation in the general form of the any differential equation. Suppose if y1 y1 is the solution. Okay, solution of ODE, and what is that? Y double dash plus px y single dash plus qx y equal to 0, then I can assume that let y2 equal to u y1 is second solution. Okay, then what will happen? I will write y2 single dash, and that will be u dash y1 plus u y1 dash. Similarly, if you write y2 double dash, it will be u double dash y1 plus 2 u dash y1 dash plus u y1 double dash. Now you can plug this into this, so you will get u double dash y1 plus u dash 2 y1 dash plus p y1 plus u y double dash plus p y1 dash plus q y1 equal to 0. Can you tell me what is this? Tell me, what is the value of this? What is the value of this? This will be y1. What is the value of this? Tell me. This will be 0 because I have already assumed that y1 is one solution of this. So which means that this y1 should satisfy this differential equation. So that's why it will become 0. Okay. And the same thing happened here also. If you simplify this, then other term will become 0. So that's why you can see that here other term will be cancelled out. Okay, so the same thing is happening here also, and I will use again the same thing. Let u dash equal to v. Okay, then it will become v dash y1 plus v2 y1 dash plus p y1 equal to 0. Similarly, if you rearrange this, you will get dv by v, okay, equal to minus times 1 divided by y1 2 y1 dash plus p y1 dx. Okay, any problem here? Tell me. Now if you integrate both side, you will get ln mod of v equal to, this will become what, minus 2 y1 dash divided by y1, okay, minus p dx. Okay, so then ln v equal to, this will be, when you integrate it, not integrate it inside also, this will be nothing but minus 2 times ln mod of y1 minus p dx. Can you write it? Tell me. This will be actually outside of the integral. So this will be 2 times ln y1, okay, minus p times dx. Tell me. Here, since p is a function of x, p is a function of x, so that's why right now we are not able to integrate it. Okay, then what will happen after this? Tell me. I can write ln v multiply 2y1 square equal to what? Minus p dx. Okay, and this will be v 2v y1 square equal to e raised to the power minus p dx. Okay, then you will get v equal to 1 by 2y1 square e raised to the power minus p dx. Okay, 2 will be, because I have already taken square, so here 2 will not be here. It's fine? Tell me. Now again I want to get u. So u is what? U is what? Tell me. U is what? I have assumed what? U dash equal to v. So u dash equal to v. So if you want to get u, then it will be integral of 1 y1 square e raised to the power minus p dx and dx. So this is u. Now I want to get y2, and y2 is what? y1 times this. So this is the second solution. Okay, there is an application. I will show you why I have derived this form. I will show you. Okay, any problem? Tell me.
No, sir.
Okay, now let's go to the homogeneous ODE with constant coefficients. Constant coefficients means what? Px will be a constant, Qx will also be a constant, and since it is a homogeneous, which means that Rx is 0. So what is that? Y double dash a y dash plus by equal to 0. So now I will try to solve this kind of differential equation. Okay, so to solve this differential equation, we have to know one kind of differential equation, solution of one kind of differential equation. And what is that? As we already know, that the solution of what is the solution of this differential equation? Tell me. It's a first order. What will be the solution of this differential equation? Tell me. Is it correct or not? Is it correct or not? How to get it? It's a clear. Y dash I can write dy by dx plus ky equal to 0. So when you transfer it, you will get dy by y equal to minus k dx. Integrate it, you will get ln y equal to minus kx plus c. You will also get plus c. So you will get it what? Y equal to e raised to the power minus kx plus c. I can also write e raised to the power c times e raised to the power minus kx. So I will assume that this is a constant c1 e raised to the power kx. So you can see that the solution of this differential equation is this. Now you will ask, but C1 is also coming. But the thing is, from the fundamental theorem, which I have already proved, that if this is one solution, which means that its linear combination will also be the solution. Okay, so this is the solution, which means that linear combination means what? Since there is only one function, so constant times this will also be the solution of this differential equation. Okay, so I will use the benefit of this result. Okay, so what will I tell is, if the solution of this differential equation is this, then similarly I will assume that let y equal to e raised to the power lambda x is the solution of this differential equation, is the solution of I will assume that let this is the solution of this differential equation. So what will I do? I will first I will get first derivative, that will be lambda times e raised to the power lambda x. What will be the second derivative? That will be lambda square e raised to the power lambda x. Now plug these two into here. So you will get lambda square e raised to the power lambda x plus a times lambda e raised to the power lambda x plus b e raised to the power lambda x equal to 0. Okay, now you can see that e raised to the power lambda x is a common. You will get lambda square plus a lambda plus b equal to 0. Since e raised to the power lambda x cannot be equal to 0, which means that this term has to be 0. Okay, now since you can see that it is actually quadratic equation, and you will get two roots. And what are those? Lambda equal to, what is the root of the quadratic equation? Minus b plus minus b square minus 4ac divided by 2a. So similarly I will write it minus a plus minus a square minus 4b divided by 2, which means that the first root will be minus a plus a square minus 4b divided by 2, and second root will be lambda 2 equal to minus a square minus 4b divided by 2. Okay, so this is the solution of this quadratic equation, and we have assumed that if lambda e raised to the power lambda x is the solution, if you substituted that, then you got two lambdas, which means that y1 equal to e raised to the power lambda 1x is one solution, and y2 equal to e raised to the power lambda 2x is another solution. Okay, now then what will be the general solution? The general solution will be what? Linear combination of c1y1 plus c2y2. Okay, but this is not the whole story. This is not the whole story. The whole story is depends on what kind of this root is. Okay, so we will consider three cases. As we already know that for quadratic equation we get three cases, and what are those? If discriminant is greater than 0, which means that, what is that? If a square minus 4b greater than 0. If that is the case, which means that lambda 1 and lambda 2 are real numbers. Lambda 1 and lambda 2 are real roots. Then in that case I don't have any problem to write something like this. This is the solution if all roots are real. But what if discriminant is less than 0, which means that a square minus 4b will be less than 0? Then in that case lambda 1 and lambda 2 are imaginary roots. Then what will be lambda 1 then? Lambda 1 I can write minus a plus I times 4b minus a square divided by 2, and lambda 2 will be minus a minus I times 4b minus a square by 2. I have taken minus 1 as a common, so that's why it will become 4b minus a square. Okay. Now, then what will be the solution? The solution will be something like, if I assume that omega is something like this, 4b minus a square by 4, which means that b minus a square by 4. If I am assuming that this is the omega, then lambda 1 equal to what? Lambda 1 equal to what? Minus a by 2 plus I omega, plus minus it is first root, it will be plus, and what will be the second root? That will be minus a by 2 minus I omega. Are you guys with me? Tell me.
Yes, sir.
Okay, then what will be the solution? Solution will be C1 e raised to the power minus a by 2 I omega times x plus C2 e raised to the power minus a by 2 minus I omega times x. And you can see that I can take common e raised to the power a by 2 x, and this will become C1 e raised to the power I omega x plus C2 e raised to the power minus I omega x. Okay, now I will use the Euler identity, and Euler identity says if this is an exponential form, then you can write cos omega x plus I sin omega x. Okay, I will use this identity and I will substitute here, so you will get e raised to the power minus ax by 2, it will become C1 cos omega x plus I sin omega x. Similarly, here I will write cos omega x, since you can see that since it is a minus times, but I know that cos minus x equal to cos x, but sin minus x will be minus sin x, so it will be minus I times sin omega x. Okay, so it will become e raised to the power minus ax by 2. Now you can see that C1 C2 is a common, it will become cos omega x. Similarly, here you can see that I C1 minus I C2 is a common, and you will get sin omega x. Okay, now I will take this as capital A, this as a capital B, because these two are constants. So we will get ax by 2 a cos omega x plus b sin omega x. So this is the solution when roots are imaginary. Okay, now if you want to draw a graph of this solution, you know what kind of graph you will get? You will get solution like this. This kind of solution you will get if you draw the graph. Okay, and you can see that this amplitude is actually diminishing. Okay, and you know what kind of curve this peak is passing through? this peak. If you draw this function, you will get the graph something like this, and this graph, this the function of this curve where all peaks are touching, that is nothing but e raised to the power minus ax by 2. So you can see that this function is nothing but a periodic function. This function is nothing but a periodic function where a time period will be nothing but 2 pi omega, which means that all this second peak, the distance between these two peak, the distance between these two peak will be nothing but 2 pi by omega. But you can see that this function has been multiplied by this, and because of this the height of this peak is decreasing, and all those peaks are actually touching with this graph. Okay, but this, the graph of this function is, you know what, that is minus times e raised to the power minus ax by 2. Now you will ask why this is a minus times, because there might be some case where this whole function can result minus times. So that's why the graph of this whole function will be actually inside of these two functions. And because of this function, it actually damping, because of this function is actually damping, it is showing the damping effect. Damping effect means what? This peak is decreasing by the time. And why it is happening? Because of this function. What if this function is not present? If this function is not present, then the graph will be something like this, periodic. But because of this diminishing function, the time period will remain same. The distance between each peak will always be 2 pi by omega. Okay, so this is the whole story if the discriminant is less than 0, when roots are imaginary. But what about the third case? Third case says if discriminant is 0, which means that if a square minus 4b equal to 0, then it is the case of repeated roots. This is the case of repeated roots, and in this case you can see that here lambda equal to lambda 1 equal to lambda 2. Then you can see that one solution will be what? E raised to the power lambda 1 x, and other solution will also be e raised to the power lambda 1 x. But I have already told you that these two solution has to be linearly independent. But you can see that these two are same, which means that these two functions are linearly dependent, which means that we cannot accept this solution. So what? We have to find other solution. And how we will get it? How we will get it? Tell me. How can we get it? Other solution. You guys has to respond something. It cannot work like this. Are you guys here or not? Tell me.
Yes, sir.
How can we get other solution? You can see, can you see that these two are linearly dependent solution? Yes or no? I told you, if you have one solution and you want to get other solution which are linearly independent to each other, then we have to use this, whatever I have derived. Can you see that I already know one solution? Now I have to get other solution. And what is that? Y2 equal to this. Now I will use this to get other solution, because I cannot accept this because these two are linearly dependent. So y2 will be what? 1 divided by, what is that? What is that? I will use directly this. That is nothing but y1 okay. So y2 will be e raised to the power lambda 1 x integral 1 divided by y1 square, which means that e raised to the power 2 lambda 1 x e raised to the power minus, and what is p? What is p in this case? P is nothing but this a. P is nothing but a dx dx. Okay, so y2 will be e raised to the power lambda 1x and 1 divided by e raised to the power, what is lambda 1? Lambda 1 is nothing but minus a by 2. Can you see that? Lambda 1 is what? If roots are repeating, which means that lambda 1 equal to lambda equal to lambda 1 equal to lambda 2 equal to nothing but, you have to just equate this as a 0, because these roots are repeating. So which means that all lambda are nothing but minus a by 2. Okay, so that will be minus a by 2. So I will substitute minus a by 2. This will be minus a x dx. So y2 will be e raised to the power lambda 1x. Now you can see that this will be cancelled out. That will be 1 dx. So y2 will be e raised to the power lambda 1x times x. So other solution will be x times e raised to the power lambda 1 x. That is nothing but x times y1. So what will be the complete solution? Complete solution will be c1 e raised to the power lambda 1x plus x times c2 e raised to the power lambda 1x. So this is the solution. You can also write c1 plus x c2. So this is the solution if roots are repeating. So nothing you have to derive, you have to just find one root and just plug it here. Now there is an application here. This case is called critical damping. Critical damping. Because in this case roots are repeating, and this case is called under damping. This is called under damping. In terms of vibration, when you study theory of machine, then you have to pass through all these equations, and this form is actually called over damping. So there are three cases: over damping, under damping, and critical damping. Okay, now let's take one example to solve this kind of problem. Any problem here? Tell me. So let's take one example.
No, sir.
Suppose you have one differential equation is something like this. Okay, and there is a initial bond, this is initial boundary problem, and initial condition is if y0 equal to 3 and y dash 0 equal to minus 3.5, then what will I do? I will assume let y equal to e raised to the power lambda x is the solution of this differential equation. Okay, then I will substitute the first derivative and second derivative into this, then you will get lambda square e raised to the power lambda x plus lambda e raised to the power lambda x plus 0.25 e raised to the power lambda x equal to 0. Since e raised to the power lambda x cannot be equal to 0, then you will get lambda square plus lambda plus 0.25 equal to 0. This equation is also called as characteristic equation. Now find roots. Then you will get lambda square plus 2 times 1 by 2 lambda plus 1 by 2 square equal to 0, and that will be lambda plus 1 by 2 square equal to 0. You will get lambda equal to minus 0.5. Now you can see that it is a case of repeated roots. Okay, then directly you can write what will be the solution. Solution will be e raised to the power lambda x, that will be minus 0.5x c1 plus x c2. So this is the general solution. Why it is a general solution? Because since we don't know what is the value of c1 and c2, okay, so there is actually family of equations, so that's why it is called general solution. Now if you substitute this initial condition, now substitute that, it is saying y0 equal to what? Y0 equal to 3. Substitute here, you will get 3 equal to, this will become 1 c1 plus 0, so you will get c1 equal to 3. Okay, now the first derivative, you have to get the first derivative, that is nothing but minus 0.5 c1 e raised to the power minus 0.5x plus c2 e raised to the power minus 0.5x plus minus 0.5x c2 e raised to the power minus 0.5x. So the condition it is saying y dash 0 equal to minus 3.5, so which means that everywhere you have to substitute x equal to 0, so you will get minus 0.5 c1, this will become 1, this will become 1, so c1 plus c2, and this will become 0. So minus 3.5 equal to minus 0.5, since we know that c1 equal to 3, so you will get c2 equal to what? Minus 2. Okay, so what is the final solution? Final solution will be 3 minus 2x e raised to the power minus 0.5x. This is the solution, and this is actually called particular solution. Particular solution, because this is an existence of unique solution. Now you can also be confused because of that particular integral. If you study second order differential equation, I will teach you later. So there is also a term called particular integral, that is a different term, okay, but this is a particular solution because there is an existence of unique solution based on this initial value condition. Okay, so this is the solution of this problem. Okay, now if you plot this, if you plot this graph, if you plot the function of this graph, you will get something like this, because we know that at x equal to 0 the value is what, 3. So the graph will start from here, and it is also saying that at x equal to 0 the derivative is minus 3.5. The derivative is minus 3.5, which means that the tangent line, the slope of the tangent line at x equal to 0 will be something like this. Okay, so this angle is nothing but theta equal to tan inverse 3.5. Now you will say it should be negative, but I am measuring from this direction. Okay, so the graph will be something like this. This is y, this is x. Okay, so that's why it is called critical damping, because there is no such oscillation here. Okay, and when you can see that what is the value of this, what is the value of what is this x, can you tell me what is this x? Tell me. What is this x? At what x this y is 0? This is nothing but 1.5. Okay, and graph will not intersect x, but it will touch, but at infinity. When x is very large, then y will become again 0, not exactly 0 but approach to 0. Okay, so yeah, this is the case of critical damping. Critical damping. Damping why? Because you can see that because of this function this graph is diminishing. Fine? Any problem here?
No, sir.
Okay, now let's take other problem. If we have one problem like this, y dash plus 0.4 y dash plus 9.04 y equal to 0, and the initial condition is like this. Then what is the characteristic equation? Can you tell me? What will be the characteristic equation of this differential equation?
So lambda square plus 0.4 lambda
Good.
9.04.
9.04, not lambda. Okay, 9.04 equal to 0. Now you have to get roots, so you will get lambda. This time you will get imaginary root. This time you will get imaginary roots, so that will be 0.2 plus minus 3i. Okay, so the solution will be something like this, and this is called alpha, that is minus 0.2 x. Okay, a cos, this has a beta, so directly I will use it, 3x plus b sine 3x. So this is the general solution. Now I will use these two boundary conditions. So when you substitute this boundary condition, you will get b equal to 1 and a equal to 0. So the solution will be something like this. So this is the particular solution of this initial value problem. Okay, now if you draw the graph of this function, then first you can see that what is the time period of this function? Can you tell me? What is the time period of this function? Tell me, what is the time period of this function?
Two pi by 3.
2 pi by 3. Good. 2 pi by 3. Which means that periodicity will remain existing. So if this is a 2 pi by 3, then what will happen? Can you tell me from where graph will start? From here or here or what? I mean, I want to ask, what is the y-intercept of this function? What will be the y-intercept of this function? This whole function. From where graph will start? Origin, right? You can see that when x equal to 0, y equal to 0. Here also you can see that when x equal to 0, y equal to 0. So graph will be something like this. Okay. Now you can see that the peak will diminish. Okay. Peak will diminish. And what kind of function is this? Can you tell me? What is this function? What is this function? What is this function?
So e to the power 0.2.
Minus 0.2 x. And what is this? What is this? Minus e raised to the power minus 0.2 x. Okay. So yeah, this is the case of what? Which case is this? What kind of case is this? Under damping, over damping, critical, what kind of case?
Damping.
Huh?
Damping effect.
No. Which case? I discussed 3 cases, right?
Under damping.
Under damping. Because we got imaginary roots. So that's why it is a case of under damping. Okay. So yeah. So there is an application. There is an application in case of vibration problem. Okay. So yeah. So suppose you have a ceiling. Okay. Now there is a damper. Okay. And there is a spring. And there is a mass m. Okay. And the spring constant is k and damping coefficient is c. Okay. And I'm measuring all the displacement from this direction. Okay. So when you use D'Alembert principle, then you can write, if you draw free body diagram, so this will be cx dot and this will be kx. X dot means what? Velocity. Okay. This damping coefficient, because of this damper, the force acting in opposite direction on mass will be c times v. Okay. And because of that v, I am writing x dot, and because of that spring, the force, the spring will act a force kx in opposite direction of the motion of this block. Okay. So because of the D'Alembert principle, I can write ma equal to minus kx minus cx dot. So at the place of a, I can write mx double dot equal to minus kx minus cx dot. If you rearrange it, you will get mx double dot plus cx dot plus kx equal to 0. Now I will assume let e raised to the power lambda t, since I am using time as an independent variable. So I will assume that let xt equal to lambda e raised to the power lambda t is a solution. Okay, then if you substitute here, then you will get lambda square m lambda square plus c lambda plus k equal to 0. This is a characteristic equation. Okay, and you will get root minus c plus minus b square minus 4ac c square minus 4m divided by 2m. If you rearrange it, you will get minus c by 2m plus minus, so you will get c by 2m raised to the power 2 minus m by k. So 4, it should be k. Okay, so yeah, so this is the root of that differential characteristic equation. Now this is a case, there are three cases. First case, what it is says, it says if c by 2m minus k by m is greater than 0, which means that it is a case of what? Over damping. Okay, then what will happen? The solution will be xt will be what? c1 e raised to the power, I'm assuming that this as a lambda 1 and lambda 2, then you will get lambda 1t plus c2 e raised to the power lambda 2t. This is the over damping. And what is the critical damping? Critical damping will be c by 2m raised to the power 2 minus k by m equal to 0. Then what will happen? This whole term will vanish. So in that case, you will get lambda 1 equal to lambda 2 equal to minus c by 2m. Okay, then what will be the solution? xt equal to c1 plus, tell me what should be here? What should be here? Tell me, what should I write here? T times C2, right? So this is the case of what? Critical damping. Okay, and when you take under damping, so that will be c by 2m raised to the power 2 minus k by m less than 0. Then you will get imaginary solution. Okay, then you can write lambda 1 equal to minus c by, I will write a plus I omega. I will write in this form. So you will get, and what is a? What is a? A is nothing but minus c by 2m. In this case, a equal to c by 2m. Okay, and what is omega? Omega, I will write this, k by m. Okay, so what will be the solution? Solution will be xt equal to e raised to the power minus ct by 2m plus a omega t, sorry, a cos omega t plus b sin omega t. Okay, so this is called natural frequency. No, not this. This is called natural frequency, and this whole term will called as a damping frequency. In this case, it is damping frequency. I can also write another form. If you study vibration, you can also write this kind of form. This is natural frequency. And what is omega n? Omega is nothing but k by m. And what is zeta? What is zeta? That is c by cc. And what is cc? 2km. So this kind of form, this is called damping factor. Okay, so yeah, you can clearly see that this is a periodic, but because of this term the whole peak is diminishing. Fine? Any problem? Tell me.
No, sir.
Okay, so in next class I will talk about Euler-Cauchy differential equation, and also I will talk about the differential equation in this form, something like this. I will talk about this form in next class, and Cauchy-Euler differential equation. I will also talk about what is the Wronskian. Okay, here I already talked about what is Wronskian, but what is the use of Wronskian I will talk about in the next class, and the next class will be the last class of the differential equation. Then I will talk about Laplace transformation, and based on the Laplace transformation I will also talk about how to use the Laplace transformation to solve the differential equation. Fine?
Yes, sir.
Okay.
Yes, sir.
Yeah. So I will stop.